Okay, guys, welcome to today's lesson in statics. Today we're going to be covering problem 55 in chapter 3. So number 55 says, the frame ACD is hinged at A and D and is supported by a cable that passes through a ring at B and is attached to hooks at G and H. Knowing that the tension in the cable is 450 newtons, determine the moment about the diagonal AD of the force exerted on the frame by portion BH of the cable. So essentially what we're doing is we're determining the moment component about this axis A to D due to the tension on the cable going from B to H. So I've gone ahead and drawn a free ride diagram about. The free ride diagram shows point A. We have our unit vector going from A to D. We have our position vector going from A to B. We have our tension vector going from B to H. So I've also drawn these out on the diagram itself. So you look here. The green arrow represents the unit vector from A to D. The position vector is represented by the purple arrow, and of course the tension will be represented by this orange arrow here. So in the free ride diagram, we have our tension value of 450 newtons. We're going to go ahead and write down our equation for a moment. For AD, our scalar moment AD is equal to the unit vector going from A to D dotted with the moment about point A, which is due to the tension at B to H. So this would be equal to the unit vector A to D dotted with our cross product of our position vector going from point A to point B where the tension is being applied. This is crossed with the tension vector going from B to H. So we need to find each one of these components of our equation, and then we can solve for the moment about axis AD. So first up, we're going to find the unit vector AD. So the unit vector A to D would simply just be the position vector going from A to D divided by the distance, magnitude of this position vector A to D. So looking at our diagram going from A to point D, it appears in the x-axis we're going half a meter and another half a meter. So that'll be 1 meter in the I-hat direction. We're not going any dimension. We have no dimension in the j-hat direction. We're staying on this xz plane. We're not going up at all, essentially. So it'll be plus 0 j-hat. This position vector going from A to D. And finally going from point A to point D, we appear to be going 0.75 meters into the page. So it'll be negative 0.75 k-hat. Excuse me. Now to find the distance, we're simply going to do the magnitude formula for these components. So the distance right up here from A to D is equal to the square root of each one of these components squaring that together. So it'll be the square root of 1 squared plus 0 squared plus, in parentheses, negative 0.75 squared. So our distance that we can write down here underneath each one of these components, we type into our calculator. Let's go to our calculator app. We're not using vector P here. There's no force P, so we can move this calculator app up. So it would simply be 1 squared plus 0 we can ignore, plus, in parentheses, negative 0.75 squared. We'll square root this number, and we get 1.25. So it's 1.25. So this is equal to 1.25. Okay. Now we're going to divide each one of these values by 1.25. And our unit vector going from A to D is going to be, when we divide 1 by 1.25, be 0.8 I-hat plus 0 j-hat, and then negative 0.75 divided by 1.25 is negative, so minus 0.6 in the k-hat direction. So we already have our unit vector going from A to D. That's good to know. So next we're going to find our position vector going from A to B. Looking at the purple arrow going from A to B, we're going half a meter in the on the x-axis in the positive direction. And we're not going up, we're not going in or out of the page. So that's the only unit, that's the only dimension. So our position vector going from R from A to B is simply 0.5 meters I hat, and then 0 in the J, no, not going up vertically, we're not going into or out of the page, so 0 K hat as well. Now last we need to find the tension vector, this orange arrow, represented here in the diagram, going from B to H. So tension vector B to H would follows this formula equals the tension scalar value given to us is 450 newtons multiplied by the position vector going from B to H divided by the distance going from B to H. So now we're going to find the position vector going from B to H. So we'll look at the diagram again. Going from B to H, we're at 0.5 meters in the x-axis. We're going to 0.875 meters. So we're going to find the difference between those two, and that's going to be our I hat dimension. So it'll be 0.875 minus where the position we're already at in the x-axis, 0.5. And that would be our I hat dimension. On the y-axis, the j hat direction, we're going up, it appears, to point H, 0.75 meters. So we plus 0.75 in the j hat direction. And finally, in the k hat direction, it appears we're going a distance of 0.75 meters into the page. So it'll be minus 0.75 meters as we're going on the negative z-axis in that direction, or k hat. So to condense this, we're at, for I hat we have 0.875 minus 0.5, which gives us 0.375 in the I hat direction. To find the distance for B to H, we're simply going to do the square root again of the component squaring out together. So the square root of 0.375 squared plus 0.75 squared. Go back in parentheses, plus negative 0.75 squared. So we multiply this out, or square this out, we have the 0.375 number squared plus 0.75 squared plus, in parentheses, negative 0.75 squared. We'll square root this answer and determine our distance is 1.125 meters. Excellent. So now we can go back and plug in these values and get our, we have our 450 Newton value of our tension. We can plug in this position vector and plug in this distance value from B to H. We can determine what our tension vector is. So our tension vector, substituting these values in, is equal to 450 newtons. So 450 over our distance, 1.125, multiplied by our tension vector, multiplied by our position vector of 0.375 I hat plus 0.75 j hat minus 0.75 k hat. Now we're going to divide these two numbers and then multiply by each one of these coefficients for the I, j, and k direction, x, y, and z directions. So 450 divided by 1.125 gives us 400. So multiply each one of these values by 400 times 0.375. We get 150 in the I hat direction. 0.75 times 400 is plus 300 in the j hat direction. And then the k hat has the same coefficient, so it'll be minus 300 k hat. So now we have our tension vector going from B to H. We have our position vector going from A to B. We have our unit vector going from A to D. We have everything we need. We can now plug this into our formula. So write this out again. Moment AD essentially turns into the unit vector from A to D, the dot product of that with the cross product, the moment vector, about A, which is position from A to B, cross tension at B going to H. This will become our determinant of our matrix. So we have the determinant. We have across the top, we have our unit vector A to D. So in the I hat column, we have 0.8. J hat column, we have 0. And K hat, we have negative 0.6. Negative 0.6. Then in the position vector going from A to B, we have 1 dimension. We have half a meter, 0.5 in the I hat. Then 0 and 0 in the J and K hat. And finally, our tension vector going from B to H, we know is 150 in the I, 300 positive in the J, and negative 300 in the K direction. So now to solve this, we can work it out. If we were to write out our columns again and go down to the right add, up and to the right multiply and subtract. However, we can also determine this because it's a scalar product for this moment about this axis A to D. We can also use a determinant function or calculator. So the determinant, we go to second matrix. We go to edit. We can edit matrix A, make it a 3 by 3. We can enter in the values 0.8, 0, negative 0.6, 0.5, 0, 0, 150, 300, and negative 300. We can then quit, go back to matrix, go to the matrix function, go over to math, find the determinant. You choose function 1, the determinant. Then go back to the second matrix one last time and select matrix A. The determinant of matrix A tells us the moment is negative 90. We have units of Newton meter. So the moment about AD is negative 90 Newton meters.
Alright guys, thanks for joining me in another simple STEM solution video. Be sure to like and subscribe. Also, if you'd like to support this channel or have particular questions you want answered, be sure to check out my Patreon community via the link in the description below.